Thanks, Edgar. Thank you, CSC, for inviting me to give this talk. And thank you, CSC Program Committee, for being persistent. Because you know, we professors like to talk, but one thing we like to do more than talk is to put things off. So we make promises, and then we sort of forget we've made them. And a persistent program committee can, you know, really make sure that things actually happen. OK, so here's sort of an outline of my talk, which is fairly long, but there's a break in the middle where I'll say, if you want to sneak out, you can. I'm going to briefly discuss functional versus imperative programming. I'm going to introduce a variation on set notation called bunch notation, which is pretty handy for describing the kinds of things I'm describing here. And you'll find it useful for describing algorithms. And then I'm going to go into classical results, finite state machines, regular expressions, context-free grammars, LL parsing, and LR parsing, all from the standpoint of just a slightly different way of looking at things, looking at them through the lens of functional programming. So when I say functional programming, very briefly, what I mean is the idea that, as in mathematics, we apply functions to old values to compute new values. We don't keep stomping on values. So it is more of a conceptual approach, and typically it uses recursive definitions, which is translated into recursion in programs, and data structures that are nicely defined recursively, such as lists and trees. So those show up very early in functional programming. In contrast, imperative programming is stomping on values. It's based on the slow accretion of small changes, many little changes to values, in order to get computation done. It's a lot closer to what machines actually do, and it's certainly more efficient. But it's kind of low level. And typically it uses loops, while loops or for loops, arrays, and frequently modified variables, as opposed to variables that hold their values for a long time or don't even change at all. So that's sort of what I want to make a division between. And many of you know that I've recently been designing courses that use functional programming and having some success at it, and I think they work pretty well. On the other hand, I don't really want to be Mr. Functional, like doing everything in a sort of functional way, the functional go-to guy. I originally came to functional programming because it seemed to offer a chance to do things in a better way. And having discovered that that was true, at least for introductory computer science, I thought, well, let's look at other things we do in computer science and see if, by looking at them through this prism, can we understand them better? And to my astonishment, I'm discovering that, yeah, we can. And I will explain at least one aspect of that in today's talk. And that aspect is Lexing and parsing. So the idea, I'll explain what Lexing and parsing is more precisely in the next couple of slides. But the idea is this is pretty old stuff. Well, the major results were worked out in the 60s, maybe early 70s. And at that time, things were very different. Computers we didn't have personal computers. We had mainframes, and we had tiny little microcomputers that were really limited. They were slow. Memory was extremely expensive. Disk space was extremely limited. So the dominant programming languages were pretty much low-level imperative languages. Now, things have gotten a little nicer in terms of our options. We now have our own laptops, and they've got gigabytes of memory, and they're incredibly fast, and this is great. On the other hand, when we actually go to teach this stuff that was worked out in the 60s, we still teach the low-level, highly optimized end result algorithms. And this is true across our curriculum. I don't want to single out Lexing and parsing. It just happens to be the way we do it. I was presenting at an ICFP workshop last fall, and I made a statement like this, and Philip Wadler was in the audience. Philip is like one of the Don Knuths of functional programming. And he puts his hand up, and I thought, oh, Philip Wadler's asking me a question. And he said, you just said that the presentation of algorithms and data structures looks like it was frozen in the 1970s. I disagreed. Oh my God, he disagrees. And he said, Wadler went on to say, I think it looks like it was frozen in the 1950s. And I had to concede the point, because it's described in terms of while loops and arrays, which is stuff that was in Fortran in 1957. So now that we're not so scared about these things anymore, we have other ways of expressing ourselves. Let's see what we can do. So when I say we're not scared of functions, I mean just the idea of mathematical functions and the idea that a function call doesn't have to be something that's incredibly expensive, so we should avoid it. Recursive definitions, which may lead to recursive implementations, but also certain kinds of recursion we know how to turn into while loops and for loops. If we can do that, sure, let's do it, but let's not force it if it's not necessary. And lists and trees and implementations, which have natural recursive definitions. So there's going to be almost no code in this talk. I have 3 or 4 slides where there's some code showing up. But most of it, I'm just going to make mathematical definitions. And the thesis of this talk, then, is by looking at things in kind of a functional way, but really more of a mathematical way, and working from the high level down towards the lower level, we can understand these classical results in Lexing and Parsing. So I learned a lot of these results in the 70s and early 80s, originally from John Beatty, who's coincidentally teaching CS241 this term. At that point, he had just arrived as a fresh PhD, a young assistant professor, and he had his PhD in formal languages. And I learned some of this stuff from him, and then I went to the same graduate institution he attended and took a grad course in this stuff from his supervisor. So I was steeped in it fairly early, and it's in coming back to it and understanding it now that I know something about functional programming that I start to realize that there are different ways of doing things. The work I'm presenting is not my own. It's a compendium of a lot of other people's work, and I'll list some names at the end, basically. So I want to start in then on the notation. And bunch notation was invented by Rick Hayner he's currently at U of T. And it's just a variation on sets. And the idea is that we can, sometimes you have to do things with sets that look a little ugly. And we can simplify things a little bit and make for really concise, nice notation if we give up some properties and simplify some others. So the first point I want to make is that we often have to write things that look like this. S union the set with a single A in it. And you know that if you do enough of that, it starts to really look funny. And you really want to do just something like A comma S. That would be a lot easier. So we're going to do things like that. And to help us along the way, we're going to say that a singleton bunch, a bunch with one thing in it. So when I say bunch, just think set, but it's sets with certain properties. A singleton bunch is going to be identified with the element inside the bunch. So I'm not going to make a distinction between A and the set containing A or the bunch containing A. They're the same thing. We do this elsewhere. We do this when we're talking on paper about strings, right? If I say the string ABC, that has 3 characters in it. If I say A, well, sometimes I can treat that as a string of length 1, and sometimes I can treat that as a character, and I don't really draw the distinction. Now, the implementation typically does, right? The programming language is going to make a distinction between a string with 1 character in it and something of type char or something like that. Some programming languages don't draw that distinction, but I want to do that for sets in general. And to sort of compensate, my bunches are just going to be flat. I'm not going to nest bunches inside bunches. So you can think of them as containing atomic values. And then the third thing I'm going to do, and we do this for sets as well, but it's very handy with bunches, is just that functions distribute over bunches. So if I apply a function, if I have a function that's defined on atomic values, and I apply it to a bunch, what I do is just apply it to each value in the bunch and then form the bunch of all of those function values. So that makes certain things I'm doing very straightforward. I'll give you examples in the context of what I'm actually talking about. So a little bit of notation, which once again, I'm not going to give you too much in the way of examples here, but we'll shortly see a use of it. If a singleton is identified with a bunch of, a singleton bunch is identified with its element, then I don't have to draw a distinction between element of and subset of. So instead of having to say, well, okay, A is an element of S, which is the same thing as saying the set A is a subset of S. I'm just going to write A left arrow S. And I'm going to say A is in S or something like that. I'm going to continue to use standard set notation, but I'll throw in a few extra operators. So I'll use the vertical bar, or the OR bar, if you can think about that, as union. And I'll also use comma, and I already did that in drawing in the last slide. Another thing that Hayner did is he borrowed the idea of guards from early work of Dijkstra. A guard is a way of writing a conditional. So I'm going to say P, and I have to think of a way to pronounce this because I haven't given this talk before. P yields X or something like that. P with a little triangle pointing to the right. X means if P then X, otherwise the empty bunch. And what I'm going to do is put an implicit there exists on the left into guards. So suppose in this, Z is not really sort of well defined. And what I want to say is if there's some value of Z which makes the guard true, then throw X, Y into the set. And that the traditional way of writing that is up above there in set notation, but the bunch notation is just a little more convenient. And you'll see how this creates definitions which look a lot like programs, because the guarded notation is basically expressing an if then else, and what we're really doing is expressing it in a way that it's fairly obvious how to turn it into a program. So this is my slide defining Lexing and parsing in pictures. So we have some raw input which is made up of a string of characters or a sequence of characters. Lexing is the idea of grouping together words within that input. So the numbers are considered to be a lexical unit, but the operator is by itself, and then the parentheses, the delimiters are by themselves, and so forth. And then parsing is the idea of figuring out some sort of tree structure that's inherent in the meaning that we're ascribing to the raw source. So typically what we do is we have one set of functions or programs or routines to do lexing, and then we feed the output of the lexer to something which is doing parsing, and then the parser gives us the structure of the program or the object that we're trying to extract the structure of, and then we can do further computation on it. It could be that we're compiling the code that this is representing. It could be that we're interpreting that code, or this could be something like an XML file or some English text, and we're trying to extract information and process it in various ways. But it's these two sort of steps that I want to talk about today. And the traditional way to do lexing is with finite state machines. And these are traditionally presented in terms of a picture. So the state in the finite state machines are these little circles with Q's inside them. And there are 4 states in this example. And what we have is arrows between states which denote transitions based on an input character. So for example, if we're in state Q1 and we see the character A in the input, we consume it. We eat it out of the input and make the transition to Q2. And we have to have a starting point. That's indicated by the little dashed arrow. So Q1 is the starting point. And some of the states have double circles, which indicates that if you happen to finish your input while you're in a double circle state, then you accept the input. Otherwise, you reject the input. So this is a way of categorizing strings as to whether they're accepted or rejected. So it defines a language, a subset of all strings of A and B in this case. And it's not too hard to see that this is going to accept strings where the parity of the number of A's, whether it's odd or even, is exactly equal to the parity of the number of B's. So we have to sort of formally define these things because pictures are just pictures, right? We tend to define things in CS like trees in terms of pictures, but there's really some formality underneath that we have to capture. And here is the traditional formality. A finite state machine is some set of states. A set of final states, those are the things with double circles. A start state, that was the thing with the little dashed arrow. An alphabet, which was A and B on the previous slide, but could be anything in general. And finally, all these arrows. And the transition function arrows go from a state, and they're labeled with a character out of the alphabet. So formally, they're a function of those two things, and they produce a new state. And then I can talk about the language accepted by this machine, defined by these quantities, as a subset of sigma star, which is a way of saying strings of arbitrary length from the alphabet sigma. So this stands for sort of arbitrary repetition. So how do we define that? I'll give you a definition on the next slide that involves bunch notation. And the way I'm going to do it is the following. I'm going to use square brackets to define the names of functions. So this is going to be true throughout the talk. I'm going to stick something inside the square brackets. On this slide, it's a state. So Q is going to be an arbitrary state out of our set capital Q. The name of the function is square brackets Q, and then the arguments are in the conventional round brackets. And the arguments here are a string sigma. So sigma starts with S. That means string. That's going to be a convention throughout the talk. So how do I define this function Q? Well, here's the definition. If sigma, the input, happens to be the empty string, then the output of the function Q is simply the state Q. Otherwise, I compute the first transition, which is to say I take the state Q and the first character of sigma, and I feed that to the transition function delta. That gives me a new state. I take the function associated with that state, which is what the square brackets do for me, and apply it to the rest of the input. That's my definition of what a finite state machine does. I'm running the finite state machine using all of these state functions, Q, for all the Q's in the set of states. What does it mean for sigma, the input, to be a member of the language? I'm using bunch notation here. It's equivalent to take the function associated with the start state, feed sigma to that, and that should be, that produces a state, and that state should be a final state. So that is the definition of what it means for a finite state machine to accept a language, and B, it provides you with an immediate way of computing. You just have to write these functions Q. Well, how are you going to do that? Practically speaking, one way to do it is to write the function square brackets. And it has two arguments. Q is one of the arguments, sigma is the other argument. I call this the interpreted, actually it's not my terminology, it's from one of the papers I read, the interpreted interpretation. And it's pretty easy to see how this translates into code. I'll actually show you code in the next slide. But I want to contrast this with what you might call the compiled interpretation, which is that we actually have separate functions, and we write all those functions down. So here's how in scheme code we would define the square bracket function with two arguments, Q and an input sigma. Well, this is just implementing exactly what we saw before, where what I have is right here a function delta, which is computing the next state given the current state and the first character in sigma. And because this is tail recursive, it's pretty easy to turn it into a C function. So this is a while loop, and we start in the start state, and we grab characters from the input, and as long as we're not at the end of file, we just keep recomputing the current state based on the old state and the character read, get the next character, go back again. And when we drop out, I've left off the test of whether we're in a final state, because, you know, it's not so easy to figure out how to do sets and things like that in C. So there has to be some convention there. But we can make this really fast if delta here, instead of using round brackets, we use square brackets, and we make it just a lookup table, right? So then the computation of the transition function is just a lookup. It takes, you know, very little time, constant time, and that loop can be extremely quick. Well, okay, so that's the interpreted model. And how would we do a compiled model? Well, you could argue that, you know, when you actually compile this, this is also compiled. But I want to claim that there's a cool way in Scheme to write these functions. Rather than having a single run function which implements square brackets, let's actually write out the separate functions. And here's how it would be done if you had to do it by hand. I have to define functions q1, q2, q3, q4 for my example. And when I start to do that, it's not too hard to figure out one function. If I've hit the end of the input, and I'm in Q1 was one of the final states, so I produce true. Otherwise, I do sort of a case, which is a restricted version of a conditional, on the first character in sigma. And here I'm using characters are symbols, they're scheme symbols. And then I just directly call the function Q2 or the function Q3 respectively, because there's a transition on A from Q1 to Q2 and on B from Q1 to Q3. And if for some reason I hit a character which is not in the input, obviously I have to reject. Then I have to define Q2, and that takes up as much space as Q1, and then Q3, and then Q4. And I'm writing a lot of boilerplate, right? This is totally tedious coding, and this is where your copy-paste fingers get a workout. Well, you don't want to do this, right? So what I've done is sort of left off things in the slide with these ... because it would take 4 slides to put all this down. You don't want to do this. What you want to do is define some nice notation for writing down a finite state machine, like this. So I say a finite state machine is an automaton where Q1 is the start state, and then I have a brief specification of each of the states with these nice transitions, and I have true or false as to whether it's a final state or not. And I want these functions to be created for me, so that they really are functions and not, not the interpreted view. Well, we can do this kind of thing. This is called a domain-specific language, right? It's a little language for specifying finite automata. We can do this kind of thing with macros in Scheme. So here is the complete macro. I haven't left anything off this slide for generating the boilerplate that you saw 2 slides earlier from the nice specification you saw 1 slide ago. And the main thing I want to point out is that there are ... dots here, but these are actually part of the macro. They're executable code. The ones up here are specifying repetition in a pattern, and the ones down here are saying, well, when you have repetition in a pattern, there's corresponding repetition in the output. So here we're repeating these little case statements as many times as there are little transitions in our language. And here we're repeating the entire definition of one state function for as many times as there are states in our little language input. So this offers us a chance to express ourselves really nicely, but still get this sort of compiled feel. And that, I think, is about it for code in this talk. So from now on, I'm just going to be writing down math and waving my hands about what the code would look like. So traditionally, then, we go on to non-deterministic finite state machines. So if I have a regular expression, which is a concatenation, I just concatenate the 2 languages. And here's the definition of concatenation of 2 languages. And here I use a guard. If there exists an x1 in L1 and an x2 in L2, then put x1 and x2 together and throw that into the bunch. So this is the bunch of all things x1, x2 that satisfy the guard. And I also need, in order to define star, I need to say how to star a regular expression. And I already did this sort of sneakily by saying sigma star. That was the same kind of thing. But here's the definition of star. Well, what is L star? If there exists an x in L and a y in L star, we'll throw xy into the bunch. And hey, L star appears on both sides of this equation. But it's just another fixed point computation. Now this one is an infinite fixed point computation, so don't go trying to execute it, but it's a pretty good definition. And in fact, it's pretty much the classical definition of star as well. You know, if you actually formalize these things using sets, you'd go through the same process. Well, an RE is a tree. And we can simplify that tree a little bit by noticing certain things. So if I have epsilon and then a regular expression r, that's just the regular expression r. I don't need the epsilon. It doesn't add anything. If I have phi and alternated with r, the phi doesn't add anything either. If I have epsilon star, that's just epsilon. So you can do these things with smart constructors, and this becomes important a little later. But here's the traditional way of handling regular expressions. Now, they're pretty expressive. We really want to define our lexers, the parts of our language, the words of our language, in terms of regular expressions, because they're a lot more natural than finite state machines. Whether you have non-determinism or epsilon doesn't matter. These are just human readable, and humans can create them pretty easily. But traditionally, you convert a regular expression to an epsilon NFA, and then you take away the epsilons, and then you make it deterministic or simulate it. And this is a big, long, messy situation. So here's an example of how you star. If I have a regular expression R, and I create the machine for it, and then I want to create a machine for R star, well, I just do this. So I can go around in this as much as I want, or I can use the forward transitions to skip over it because I just want to get epsilon into my R star language. This is the kind of thing, and there's one of these for each operator. And this is the kind of thing that's classically done. The problem is that all these steps are quite messy to implement, and they get ugly. And when you add certain operators, it gets really ugly. Suppose we want to have a not operator. So I want to say all strings that do not start with, end with BA, BA. Then I can just take that first example and put a not in front of it. That makes perfect sense in an expressivity point of view. But when you go through this process, you start running into problems, because it's not so easy to negate a non-deterministic state machine. For a deterministic one, you can just swap final states and non-final states, and you get the negation of the language. But for a non-deterministic one, that doesn't work. So what you have to do is, when you hit one of these operators, you have to stop and convert everything down to deterministic finite automata, and that gets really expensive, because that blows up the thing you're working with. So this is awkward to begin with. It's more awkward if you throw in, and you know, from working with regular expressions in languages like Perl, you want to throw in as many operators as you want, because that makes your life as a programmer easier. So what are we going to do? Well, why don't we do the same thing we did for finite state machines? Why don't we define functions on regular expressions? So I'll use square bracket R, which consumes sigma and produces a regular expression. And here's the specification in one line. The idea is, if we can find sigma as a prefix of something in the language, so it actually, the thing in the language is sigma followed by some string gamma, then gamma is going to be in the language of the regular expression that's produced as the output of this function. So the idea is that R, when applied to sigma, produces a regular expression which represents all suffixes of sigma that can be formed by eating something which is in R, which is described by R. This is a slight generalization of what we did for finite state machines. In order to show you how to implement the functions R in square brackets, I need to define an auxiliary function, which I'm going to call nibble for nullable. I'll pronounce it nullable, I guess. And the idea is that if I take a regular expression and it actually has epsilon in the language, I want to produce the regular expression epsilon. Otherwise, I want to produce the empty regular expression, phi. And that has a pretty obvious and very simple recursive definition. in order for something which is a concatenation to be nullable, both of the pieces have to be nullable. So I can just put together the outputs of those two things. And everything is kind of obvious here. So we'll go on and define something which is very interesting, which is the derivative delta t, the derivative with respect to t of r, where t is an alphabet symbol, a terminal. So the idea is that if there's a string t alpha which is in the language, then alpha should be in the language of the derivative. So the derivative is a regular expression. And now this is pretty easy to compute recursively. So let's take a look at some of these things. The base cases are kind of trivial, so let's take a look at concatenation, which is the only really non-trivial one. What does it mean if I have R, which is a concatenation of R1 and R2? What does it mean to eat t out of the front of that? Well, I could eat t out of the front of R1 and then continue with all of R2. Or if R1 can produce epsilon, then I can't eat t out of it. So in that case, I need to eat t out of R2. And everything else is pretty straightforward. So as an example, if I want to eat beta out of this regular expression, well, this is nullable, right? The star part. So I get a part where I'm eating b out of BA, which is pretty obviously that. But also, this might produce something which is not empty, not the empty string. So at that point, I want to eat b out of that. And recursively, if you work out the details, you get a plus b star again. So now, it's pretty easy to define square brackets r sigma, and it looks like the finite state machine expression. If my regular expression is being applied to the empty string, then nothing happens to it. Otherwise, I compute the derivative with respect to the first symbol of sigma. That gets me a regular expression, and I apply square brackets of that function to the rest of sigma. And finally, what I do in order to define the language accepted by a regular expression, I apply the function r to sigma, and then I check whether epsilon is in that language, which is the same as saying that nullable of that regular expression is equal to epsilon. So this is pretty cool. And this is a really old idea. This was created in 1961 by John Brzozowski, who was coincidentally the guy who hired me here at Waterloo. He's a professor emeritus here. He's a distinguished professor emeritus, so he's retired, but he's still active. He's still doing research. He still has grad students. He still produces papers. You see him wandering the halls. And not wandering, he's going somewhere with a purpose. He's not one of these wandering types. And this is a really neat idea, and it's absolutely well suited to computation. So there's a recent study done by, well, there are two places I know where this has been implemented. I mean, I sat down and implemented it myself, but for PLT scheme, which is the scheme distribution we use in courses here, their regular expression matcher uses this idea. And also for ML, there's a traditional one called ML-Lex, and they created a version. John Reppy and Aaron Turon at the University of Chicago created a version they call ML-U-Lex, which they compared with ML-Lex. And in both cases, both of these people did comparative studies against the traditional way of doing things, which you'll see in like the Dragon book and other sources like this. And on empirical studies, this does better. as long as your constructors are smart. If you do it with stupid constructors, it doesn't do it so well. So it's pretty easy to write down the square brackets function. It's standard structural recursion on R, and R is just a tree. And it's tail recursion on sigma, just like the finite state machine is. So it's pretty straightforward. It's straightforward enough that I could give it as an exercise in CS136. People know enough by that point. If you try compiling this, you're basically building a deterministic finite automaton. And this is the thing that works really well when based against the traditional construction. It's fast enough, and it produces automata with fewer states than the traditional construction. And adding new operators is much, much simpler here. You can throw in the negation operator, no problem. It's really easy to do in the code. So why didn't this take off? Why do we go through all this pain of going through the epsilon NFAs and the NFAs? Well, my theory is because this uses recursion. It uses recursion on trees. And that's scary. You know, recursion is scary. And functions are expensive. Well, they aren't anymore. And we really should be thinking about this. And we really should be learning about it. It's beautiful. Okay, that's my section on Lexing. So if you have questions at this point, I can take them. Otherwise, we'll move on to context-free grammars. Okay, so the way that talk works out, this is slide 25. Slide 39 ends context-free grammars. That's another natural breaking point. And then the last 20 slides are on LR parsing. Those get pretty hairy. So I'll give you a chance to sneak out at any of these points. You can, get up and leave anytime you want. I will not be offended. Traditional context-free grammar. Normally you put little g's on everything, and I'm not going to do that. So I'm going to assume the grammar's fixed. And we have a set of terminals, which are lowercase letters, and this is very traditional. We have a set of non-terminals, which are uppercase letters. And I will also use angle brackets because I want to throw things into, I want to create grammars. And strings of the above are going to be Greek letters, alpha, beta, etc. We have a set of rewrite rules. Given a non-terminal, a single non-terminal, I can rewrite it as a string of terminals and non-terminals. I have a start non-terminal S, and I have a transition function. What the heck is that doing there? That's a cut and paste error. Man, forget that. Sorry. So a very simple example. S can be rewritten as ASB, or S can be rewritten as epsilon. And rewriting is just a process of repeatedly taking a string, finding a single non-terminal in it, finding a rule that applies, and doing the substitution. So we're repeatedly substituting for the S, and I apply the ASB rule 1, 2, 3 times, and then I apply the epsilon rule to get rid of the S. So pretty clearly, I'm not happy. It says parse tree here, and I should have a parse tree, but I don't. I wonder if I have an old version of the slides. That would not make me happy. Pretty clearly, this grammar produces this string where you get a bunch of A's followed by a bunch of B's, and the numbers of A's and B's are exactly the same. So the recognition question is, can we produce a particular string? Is it in the grammar or not? So given a string A, B, 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 the answer would be no. And parsing is actually producing the parse tree, which I would have a nice picture of the parse tree, but it's gone. So let's just draw the parse tree, because I can do that, right? S, A, S, B, A, S, B, and then S goes to epsilon. So that's what the parse tree would look like. And the idea is that this describes the structure of your programming language or the structure of your natural language text, and then you do some further processing on it. What I'm going to treat mostly is the recognition algorithm, and you have to take my word for it that everything I do can be extended to parsing in more or less a straightforward way. Now, at the top of the slide is a traditional definition of a rewriting step and the language defined by a grammar. So it's 4 lines of dense Greek. Let's go through it. Given a form which has an A in it, beta, alpha, gamma, we can rewrite it to beta A gamma. We can rewrite it to beta alpha gamma if we have a rule A is rewritten as alpha. So then I define a starred version of rewriting, which is kind of the obvious thing. It's a relation, right? So A is related to B in terms of can be rewritten. A can be rewritten to be B if A is equal to B, or we can rewrite in 1 or more steps. And then the plus version is A can be rewritten to beta, alpha can be rewritten to beta in 1 or more steps. And here I have an exists. There exists an intermediate gamma such that 1 step gets me gamma, and then some number of steps gets me beta. And finally, the language generated by the grammar is everything that you can get by rewriting the start symbol. That's the traditional definition. Here's a very cool non-traditional definition. I'm going to define LG as a function which consumes a string of terminals and non-terminals. And the first 3 lines just sort of set up the base cases. So if this string happens to be a single terminal, then just the language is just that terminal. If the string is epsilon, then the language is epsilon. If I can split the string into 2 pieces, then I concatenate the 2 languages together. And all of these are really setting up to do this thing over here. And these things down here are the important thing. For non-terminals, the language of things that can be rewritten from A is just the bunch of things with the following definition. If there's a rule A applies can be rewritten as alpha, then throw the language of alpha into the bunch. Now, this is a fixed point computation, but it's a little funny because, in a typical rule, A might be rewritten as something which involves a B. And so I'd have a B in here, and eventually I would get an LGB over here, and then B might be rewritten in terms of something that has an A. So I don't have just one equation. I have a bunch of equations, which are a bunch of equations in a bunch of unknowns. So it's a little more complicated than before, but exactly the same idea holds. Instead of one set into which you're throwing things, you have a tuple which you start out with emptiness everywhere, and you throw things in as necessary, and eventually you get everything. Well, not eventually, because it's an infinite computation, but the definition we gave still applies. So I just wanted to throw that in. It's a little bit of cuteness that you can, and it's really saying the same thing as the traditional form. It's just doing it in a very concise way using bunches and using fixed point computation. Little side remark, which will become important in the LR parsing part. What's the relationship between finite state machines and grammars? Well, grammars are strictly more powerful, and we can show it in the following way. We can simulate an epsilon machine using a grammar. For every state, we create a non-terminal, which I'll put that state Q in angle brackets. I throw in a rule for the start state. My start symbol S is rewritten as the start state non-terminal. If I have a transition from Q to Q prime on C, I throw in a rule that says we can rewrite the Q non-terminal as a C and the Q prime non-terminal. And an epsilon transition, I don't have anything in front of the right-hand side non-terminal. And a final state, we just rewrite as epsilon. And if you run this thing, you can see that you're basically just generating, starting from S, you generate a string by a series of transitions which when you take that string and run it through the machine, you get exactly those states that are mentioned in the non-terminals in the rewrite. And this idea comes up a little later on in the LR parsing thing, so I wanted to mention it here. So this is the core of the talk, and it's really quite lovely. It's a parser defined in 4 lines, and a pretty good parser, too. So let's go through this. What we're going to do is define functions where the square bracket thing is applied to strings of terminals and non-terminals. And it's the same idea we used with derivatives. We're going to try and eat things out of the input. So the definition, the specification for this thing is that if I take sigma, and it can be rewritten as, there's a way of splitting it into sigma 1 and sigma 2, and sigma 1 is in the language that I can rewrite gamma, the name of the function, to produce sigma 1, then throw sigma 2 into the bunch. So the gamma square bracket function eats out of its input anything that can be generated from gamma by applying rewrite rules in the grammar. This makes sense in the following way. What does it mean for sigma to be in the language? Well, I apply the sigma, I apply the start symbol function to it, and if epsilon is in the bunch that's produced, then I can eat something derived from S out of sigma and only have epsilon left over, which means that sigma is in the language generated by S. So if I can define these functions, I can do recognition. And here is the definition in 4 lines. And once again, the first 3 lines are doing what we did in our definition for grammars. They're just sort of setting up the ground rules. How do I eat epsilon out of sigma? Well, if I do that, I just get sigma. What about eating a terminal t? Well, the first thing in sigma has to be the t, and then I produce the rest of sigma. So that's kind of obvious. What about eating something x followed by beta, where x could be a terminal or a non-terminal? Well, I have to eat x out of sigma, and then I have to eat beta out of what's left. And now the 4th line is where the grammar really comes in. The first 3 lines are kind of generic. And the 4th line says, in order to eat a out of sigma, find a rule. A can be rewritten as alpha, and eat alpha out of sigma. That's it. This should be on a t-shirt. I mean, it's not quite Maxwell's equations, but it's pretty good. Now, it's not perfect. There are some flaws with it. It can't parse every grammar, and I'll discuss which grammars it can parse. And a lot of the subsequent development, a lot of the stuff you see in 241 and in 462, if it's actually taught there. It's in the notes. I don't know if it's actually taught. A lot of that stuff is fixing this up, really. So here's an example, and it's ugly, but let's just see what's going on. So we'll take our same grammar, and we'll try to eat S out of AABB. And now because I can apply this rule, and I can eat ASB out of AABB, or I can apply this rule, and I can eat epsilon out of AABB. Now, that one, I'm sort of working in parallel here. That's pretty obvious. And then that just sort of follows down. The non-trivial thing is to eat ASB out of AABB. And here I say, well, I eat A out of it, and then I eat SB out of it. Eating A out of something is pretty obvious. I just get ABB. And I have to eat SB out of that. And my claim is all of that just gets me epsilon. And here's the reason, and I start skipping steps as I go through this. In order to eat SB, I eat S out, and then I eat B out. So that B continues all the way through. How do I eat S out? I eat ASB, or I eat epsilon. Eating epsilon gets me ABB, but if I take ABB and I try to eat B out of it, it won't work. So that just becomes empty, and it goes away. But on the other side, I have an SB. If I'm eating SB out of BB, well, I have to eat the B I mean, I have to eat the S, and then I have to eat the B. So the S goes inside, and now I do it one more time, and keep simplifying, and I eventually get down to eating B out of BB, and then eating B, and that gets me epsilon. And this sequence of things, if you sort of draw it out as a tree, is basically what you would do is if you took these equations and implemented them as a function. So we can implement the square bracket function, and it has two parameters, a string, which turns out to be just sort of the right-hand, a suffix of the right-hand side of a rule, and the input. And, well, we're creating bunches, right? So in the implementation, we have to have some way of representing bunches. And this is where functional languages do better because they have lists. Of course, you can do this in an imperative language, too, if you have some data structure which supports bunches, which is just a set. It's a flat set. So a list or a hash table or whatever, you know, your favorite data structure will typically work for this. So with lists, you can implement this, and you can speed some of these things up. This is pretty clearly, you know, just sort of applying things. It's like a fold, for those of you who know what folds are. So with the help of abstract list functions, you can get this thing down to a remarkably small amount of space. I'll discuss that in a little bit when we go a little further. Here's a problem. Left recursion. So S can be rewritten as SA, S can be epsilon. Now, it's not unreasonable, right? So I can say something like that. So this is going to generate me a string of A's. But when I apply the definition, S can be rewritten as SA. So I have S applied to sigma is S applied to sigma and then eat A out of that. Well, that's not going to work, right? Immediately we're going to go into an infinite loop. We just keep trying to apply S to sigma over and over again. We never make any progress. What do we do? Well, we can rewrite this grammar to eliminate left recursion, right? It doesn't have to look like this. And it's pretty obvious how to do it for this simple grammar. And you can mechanize this process. There are two problems with that. One problem is that the resulting grammar is just less natural, right? We want our grammar to express the structure of our language, the structure of whatever it is we're recognizing. If that is unnatural, we run the risk of doing it wrong. In other words, if we do the translation ourselves, we risk making a mistake. If we do it mechanically, there's sort of this extra step involved, and the second problem shows up, which is that parse trees have the wrong shape. The way left recursion naturally arises is from left associative operators. We want A plus B plus C plus D to mean add A plus B first, then add C, then add D. Now, you might say, what difference does it make? This is addition. It's associative. Well, addition is associative, but not with 32-bit integers. No, it isn't, right? And you might have arranged this so that you don't get overflow, but if you do it in a different order, you will get overflow. So we really do want to depend on this. And if I made these minuses, that's not going to be, that's not associative. If I say A minus B minus C minus D, you don't want to do the C minus D first. So there are places where you really want it to be left associative, and it turns out that a left recursive grammar is the natural way of doing that. If you create a right recursive grammar, the parse tree is slanting the wrong way, and it'll try to do the right-hand side computation first. You can fix it up, but that involves munging trees, and it's messy. We're going to come back to this problem. For the time being, we're just going to avoid left recursion and say, well, what can we do if we don't need left recursion? Second problem is running time. Let's take a look at this. S can be rewritten as ASS or epsilon. Well, pretty clearly, this just generates strings of A's, right? But you hand it a string of 50,000 A's, and it will take one off and then basically try all possible ways of splitting it up. in the other two pieces, and it'll keep doing that over and over again. It's like the Fibonacci, the naive Fibonacci computation. It's just going to keep recomputing things. Yeah, okay, so challenge. How much time does it actually take? What do I mean by exponential? What is the actual running time of this thing? How many different parse trees are there for a string of NAs? That's an interesting question you can think about. But the solution is actually lovely, and it's something we do in 136, memoization, which is, as you're computing a function, keep a table. Check to see if you've computed it before. If you haven't, then go through the computation, and when you get the answer, stick it in the table. So next time you try to compute it, you don't have to. If you memorize a Fibonacci function, then naive recursion, boom, linear time. And something similar happens here. Well, how much time does it take here? The number of function names is non-terminals and suffixes of rules, so that's a constant because the grammar's fixed. The number of arguments, well, if the input is of length n, then there are n of them, so order n arguments. But an entry is a bunch, and it's basically a suffix of the input, right? It's a bunch of suffixes of the input, so it could be a size n as well. And how do you compute it? Well, in doing something like this, you get a bunch here, and then you apply beta to each thing in that bunch, and then you stick all those bunches together. So you have to throw out duplicates and so forth. It could take n squared time. So the resulting time complexity, if you multiply it all up, is n cubed, and the space complexity is n squared. So this thing is a parser which works in cubic time and quadratic space. And it's not a bad parser. It's pretty small. The first person who noticed this was, in modern times, who noticed that this was applicable to functional programming was Peter Norvig, who in a paper in 1991 did this and then produced an implementation from the four equations I showed you, making use of, his implementation was in Common Lisp, so he used built-in functions from Common Lisp. His basic parser was 15 lines long, and the memoization routine, which worked to memorize anything, was another 10 lines. So, you know, it could fit on a screen if I use a small enough print. And it's Common Lisp, though, so I didn't put it in, because everyone here knows Scheme. Some people may know Common Lisp, but this is cool. Incidentally, I went to grad school with Peter Norvig. That's just coincidence. He's now head of Google Research. Okay, let's head for LLK parsing. And the idea is, well, what if this is too much time and space? Well, let's use the next character in the input to try sort of. So the problem with some of these things is that it tries something. So let's take a look at something like this. It tries to eat something out of the input, but then this computation is going to fail, and we know it's going to fail. So there's hardly any point. This is the kind of thing that you want to do. You want to not do computations that you believe are going to fail. And in this particular case, if nothing in the language generated by alpha starts with the first character of sigma, then we shouldn't try rewriting A as alpha, because it's pointless. And that's all well and good, but there's another complication, which is that alpha might rewrite to epsilon. In which case, we need to check something a little more complicated. We need to check if the first character of sigma, which is not eaten by alpha because alpha is rewritten to epsilon, if that first character can follow A, because A has been rewritten to epsilon. So what we're going to compute is something involving first and something involving following. Utility predicate, we define nullable of the right-hand side of a rule. So alpha here is a string of terminals and non-terminals. And this is the obvious definition of that string can be rewritten to be epsilon. Now, it's the obvious definition, but I have things on the right-hand side which I have things on the left-hand side as well. So once again, I have a set of equations in variables, in unknowns, nibble A for A being a non-terminal. And that's a finite fixed point computation. Every time this happens, when I say finite fixed point computation, in the classical presentation, they stop and they add things into sets with while loops. And they never point out that it's exactly the same as the last time they stopped and added things to sets with while loops. For use in the first condition, we define the predicate first of alpha, where alpha is a string of terminals and non-terminals. And the specification is up there. It says, if we can rewrite alpha to be something starting with t, like t beta, then produce t. And the computation is the obvious computation, and it's a finite fixed point computation. This is all just classical results restated in this new language. Same thing for follow. The specification for follow says, well, if I want to compute the follow set for x, if I can rewrite the start symbol so that x appears somewhere in it, so it's alpha x beta, and the first thing in beta is a terminal, then that terminal can follow x. Then we have sort of the obvious implementation of follow, and it's a finite fixed point computation. Now we get to modify our recursive descent parser to take account of these things. And the only change is this line right here, which says we apply a rule if the first thing in alpha is the first thing in sigma, or alpha can be rewritten to epsilon, and the first thing in sigma can follow A. That's the definition of LL1. A grammar is LL1 if this is deterministic in the sense that there aren't bunches anymore. There's only one thing you can do at any one point. There's at most one rule making the guard true. And to get LLK, you just do this same idea with first and follow sets, which are defined on looking k ahead instead of just one ahead. Now, this is not the way it looks when you learn about LL parsing in a traditional presentation, even in 241. So how do you get the traditional approach? All it does is it pulls out the recursion stack and makes it explicit. And then you can use a while loop. That's really all it is. The stacks in conventional parsers, half of them are just recursion stacks. And because you can't see that there's a recursion going on, there's this mystery involving this stack. And the proofs get a lot harder. Proving all the stuff I just said, I didn't go into that, but the proofs are a few lines long because the mathematics hasn't been deconstructed. Okay, this is the second breaking point. Before we go through LR parsing, and I have 20 dense slides left, so this is for the hardcore people, I wanted to mention some of the things that are not classical. So there's a nice tool out there called Antler, which implements what they call LL star parsing, where they try to sort of, if you're allowed unlimited look ahead, then LL works just fine, but you shouldn't look ahead in an unlimited fashion. It turns out that most of the time you can disambiguate with various tricks. So Antler implements LL parsing in a nice way, and it's a tool you can download off the internet and work with. It's pretty interesting. More recent work, something called a parsing expression grammar, which merges the ideas of Lexing and parsing. So it doesn't really make a distinction. And it throws in regular expression syntax into grammars. And that sort of takes care of, if you treat it properly, it takes care of a lot of the left recursion problems, although there's still problems with left recursion. And there's a very interesting method of parsing called pack-rat parsing, which is based on parsing expression grammars. The idea of pack-rat parsing is it uses two things. It uses memoization, and it uses lazy evaluation, which is you can simulate in functional languages like Scheme, and it's built into functional languages like Haskell. And the idea of pack-rat parsing, it can parse a parsing expression grammar in linear time, but it takes linear space. And this would be, game over in the old days where we didn't have much memory. But nowadays, it's not necessarily a bad thing. And finally, I want to mention the idea of parser combinators, which are an idea. A combinator is a function which operates on other functions. So you can start out with little tiny functions like see if you can eat A out of the input. That's a function. And then you can have a concatenation combinator which takes two of these functions, an A function and a B function, and produces something which eats AB out of the input. And if you throw in a rich enough library of combinators, you can build tree expressions of these combinators, or even write a little domain-specific language which describe what it is you're trying to parse. And that's maybe a much more natural way of doing things than grammars. And again, that works well in languages which have memoization and lazy evaluation. So at this point then, again, if you are willing to stay, the next 20 slides take us to LR parsing, which is, you do learn about it in CS 241 and in other courses. But the way you learn about it is you see the end result. I am going to take us to that end result from a series of steps that build on what we've learned. And I won't put all the details in, but there'll be enough that you can get the idea, and I can point you to where you can get all the details if you really want. Are there questions on what I've done up to this point? Okay, let's go. The idea then here is, well, let's start off with a particular grammar transformation. And the goal of this transformation is to ensure there's at most two non-terminals on the right-hand side of any rule. You can do this with, this is called Chomsky normal form, right? But this is a particular way of doing it, which we're going to build on. And the idea is, we're going to create new non-terminals which are in angle brackets, and they're of the form, take a rule and stick a dot into the right-hand side. And this is called an item. That's the classical way of talking about it. So I'm going to do the following. 3 sets of rules. Given a non-terminal A, which can be rewritten as alpha in the old grammar, in the new grammar, I'm going to rewrite it as A arrow dot alpha. Then I can move the dot over an X and generate the X. And finally, I can take a non-terminal where the dot's all the way to the right and rewrite it as epsilon. It's not too hard to see that this grammar, this new grammar, and the old grammar define the same language. And the new grammar has at most 2 non-terminals on the right-hand side. In fact, at most 2 symbols on the right-hand side. Now, if we hit this with recursive descent, we get the following 4 equations. And that's just taking the ideas of recursive descent and just applying them to this grammar. Now, there are 4 rules, but we don't need 4 rules because we can inline T and A where they appear. And the problem is that the rule with the X in it, X could be a terminal or a non-terminal, so that splits into 2 rules. But we get 2 rules out of the 3rd rule and 1 rule out of the 4th rule. And this is a version of that where all my bracket functions have item names. And now I basically throw in a new rule with a new start state, start symbol S prime, and then I apply the S prime rewritten as dot S function to the input sigma, and if I get epsilon out, then sigma is in the language of S. This is really recursive descent that's just phrased in a different way. You can kind of see what's going on a little more. So it's still n cubed time, n squared space. It still has problems with left recursion. We need a better grammar transformation. Now, there's a way of doing this as well, classically. Greibach normal form is a way of eliminating left recursion. But there are many ways of doing it, and I'm going to choose the way to do it that leads us towards LR parsing. So we say that A is a left corner of alpha, where alpha is a string of terminals and non-terminals. If we can rewrite alpha, but just the leftmost symbol, and get something with an A on it at the front. So I'm going to abbreviate that with the abbreviation LCA alpha, which means A is a left corner of alpha. We can rewrite alpha, but only the leftmost symbol, and get to something which starts with an A. So on the next line, there's a definition of a formal definition of this, and it's got an LC on the left and an LC on the right, and it's another fixed point computation. And it's a finite one, so that's great. So we have these angled things with items. We're going to add another kind of non-terminal, x, comma, I don't think this is right. I think it's x, it should be like this. And the idea is this is like the item non-terminals before, but x is involved. We've seen alpha intuitively in the parsing thing. We hope to see beta. We want to move that dot all the way across beta. And x is a left corner of beta. So x is a possible first thing we'll see after the dot. If we use this, we can create a grammar fg which is not left recursive, and it's equivalent to g. It has 5 types of rules. Type 1 introduces dots. Type 2 says if we have this x is a left corner thing, then we can just get rid of it. Type 3 says if we see a t in the input intuitively, then t is going to be a left corner. So let's throw it into the non-terminal. Type 4 is saying, well, if x is a left corner and x appears as the first thing in a rewrite of b, then intuitively b could be a left corner, but we have to check. And finally, type 5 just says we've got the dot to the right-hand side, we're done. And the claim is this is not left recursive if under a technical condition to A by a series of rewrites. So the grammar is not cyclic. And if the grammar has no epsilon rules. The epsilon rules will throw in a 6th condition, which looks like type 4, but it's got epsilons in it. I just wanted to leave it off the slide. The example, if we take that simple grammar left recursive, s rewritten sx, s rewritten as y, and I go through all these things, I get this total mess, which you're not going to be able to understand. Let's take a look at some parse trees. So way up in the top right corner is the parse tree for the original grammar for the string yxx. And this big mess here is the parse tree for yxx in the transformed grammar. But you can see that that one is slanting the wrong way. It's slanting the right way in terms of if you do a recursive descent into it and then you start coming up, evaluating bottom up, you'll do the yx combination first, and then you'll combine the result of that with x. So you get the sort of the proper kind of left association, and that makes it clear that one place where you really want left association, it's very important, is in sequencing statements, right? The idea of sequencing statements is left associative, so that's a place where that really comes up. But let's see what's happening over here. Well, we get these funny sort of things which are just cleaning up, and there's a clump of that here, there's a clump of that here, there's a clump of that here, but we also get the y sort of much more quickly than we do over there. And we get the x and the other x, and then everything gets cleaned up. And what's happening, and you'll have to take my word for this, that if you descend through this and then start going back up and do the right thing at the right spot, you can recreate that thing over in the top. So our goal is to get the thing up in the top right. We can do that by descending into this thing and going back. So this is a recursive computation that is going to do the right thing if we can make use of it. So we apply recursive descent to this. So we have two types of functions now. We have functions with just items and functions with left corners in them. I'm going to rewrite the functions with left corners using this bar notation. And the result, again, you have to go through the details, but it's not too bad, is the following. This is known as a recursive ascent parser. And its definition is fairly straightforward. It's two sets of mutually recursive functions. And you can sort of see what's going on. Well, so if we're trying to move over beta and we have something in the input, the first thing in the input is a left corner of beta, well, then let's call the left corner function, where the left corner is the thing we see in the input, and the rest of the input is the rest of the input. And the left corner function basically tries to climb up. So the first left corner we'll see is a terminal, and then we'll start climbing up the tree by rewriting that terminal in terms of terminals that come closer and closer to something that's closer to the start symbol, if you will. And that's basically what's happening here. When we identify something that can produce X, then let's make that, and if that's a left corner, then let's use that as a left corner argument in an application of the appropriate function. So because it's sort of climbing up from the bottom of the tree, it's called recursive ascent, to contrast it with recursive descent. Memoized, still the same problems. N cubed time complexity, n squared space complexity, but we've gotten rid of the left recursion. And you can throw in, as I said, if you do the right thing at the right point, you can get a compact representation of all possible parse trees. The advantage of this is that it will parse any grammar. It will parse ambiguous grammars. Now, in a programming language context, we don't want an ambiguous grammar. But in a natural language processing context, that happens all the time. Natural language is ambiguous. And what you want is, give me all possible interpretations, and then there's some AI stuff which deals with them. So this is pretty useful in an AI context. You want to be able to do these things. Right? If you throw an ambiguous grammar at a classical LR parser, it'll just give up. So you can't do that. So there are places where LR parsing is just not going to work. So what's the idea of LR parsing? We restrict the set of grammars so that, you can't do it on any grammar. And the idea is by doing that, we get down to linear time and space complexity. And we need one more idea in order to do that. And this is where, if you see a gun in the first act of a play, it better be fired in the third act, right? So I talked about how you could simulate a finite state machine with a grammar. This is where I fire that gun. So we simulated a finite state machine by a grammar. Let's take a look at some of the rules in this transformation. I went over them pretty quickly, but one of the rules said, well, we can generate T and then let T be a left corner. That was the type 3 rule. That's the same idea as a state transition on T. That's what we did in our simulation. Here, where we're moving the dot over the X, that looks like a state transition on X. And finally, when we throw in a new rule, there's nothing generated here. That looks like an epsilon transition. And in fact, that analogy kind of holds. It's not a perfect analogy, but if a rule is like a transition, and not knowing what rule to apply is like not knowing which transition to make, then let's use the idea from a non-deterministic finite state machine. Instead of our bracketed functions having a single item inside, let's put a bunch of items inside. We don't know what to do. Let's do everything in parallel and see how it turns out. And a bunch of items is even called a state in the classical presentation. So they really had this idea in mind. So for each state, which is now a bunch of items, we'll define square bracket function of that state with kind of the obvious interpretation. If there's an item in the state, and what we want to do is take that item, it's of the form A is rewritten as alpha dot beta, and we want to basically eat beta out of input sigma and produce what's left over. But also we'll label that with we use to eat it. If we do that, then we throw in the if we throw the thing we're trying to recognize into this function, and what comes out is pretty obviously the same thing, but with epsilon as the second argument here, then we've eaten all of the input, and the input is in the language. This is our definition of the epsilon transitions. It's basically saying, well, instead of trying to hop over the B, let's do an epsilon transition to something which is starting to rewrite B. Then we discuss reach in exactly the same way. Classically, it's called predict. And you can create a definition which is non-recursive, which doesn't involve this kind of discussion. You can do it in terms of left corners, because we already did the requisite fixed point computation for left corners. And then we get a transition function, which is the transition function of an automaton. The automaton consumes a state, Q, which is a bunch of items, and a symbol X, which could be a terminal or a non-terminal. It basically says, well, grab all items in the reach state, in the reach of Q, and move the dot 1 over. This is known as the LR0 automaton of the grammar. And then we hit it with recursive ascent. So here's the specification of the auxiliary functions. If we work out all the details, and that takes, a page or so, we get this LR0 parser. Why is it an LR0 parser? Well, there are grammars which are LR0, and they are LR0 because this process is deterministic. That is, all the bunches are single valued. You never have this returning more than one thing. So that's LR0. And what are the possible sources of non-determinism? Well, it could be that we're throwing in several things, and it could be that there are several of these things that are possible. So that's one place. If a state Q has more than one item where there's a dot on all the way to the right, then we have non-determinism, and this is classically a reduce-reduce conflict. The other place is right here, where we have an application of goto. But we could also have, so at this point, Q calls a Q bar, and Q bar does a goto transition. But if we also have these kinds of things happening at the same time, we'll get several things thrown into the bunch. So if a state Q has only one item with the dot all the way to the right, but there's a possible goto, and it's a goto on a T, and T happens to be the first thing in the input, then we don't know whether to eat that T, make it a left corner and keep going, or do the epsilon transition. And this is known as a shift-reduce conflict. The shift is eating the T, and the reduce is doing the epsilon transition. So that's what happens if you try to feed something which is not LR0 to the LR0 construction. For LRK, you can throw in look ahead, and it uses first and follow sets in basically the same way. If you take the recursive descent applied to the grammar and throw in the look ahead, you'll get LRK. Now this doesn't look anything like the classical presentation. What you see in the classical presentation is kind of the end result. So how do we get from this thing, which is a bunch of mutually recursive functions, to the classical presentation? I'm not going to say everything, but here's basically the idea. First of all, make the recursion stack explicit. That's what's known as the state stack in the classical presentation, which means you can have a while loop, which is either eating the input or doing something, rewriting the stack in a certain way. The input argument is also growing and shrinking in a stack-like way. And in a scheme implementation, it would be a list, and a list is just a stack. So that's what's known as a symbol stack in the traditional presentation. And if you throw in items and extra arguments, then you can just sort of read the input a character at a time and not ever have to sort of treat input explicitly. So that this turns it from an offline parser to an online parser. And then finally, you tweak things certain ways. You can talk about, well, you don't ever need to push items onto the symbol stack, because when you're doing that, you're at the right-hand side. So what you do is you end up, if you trace through what you have to do, you end up popping things and then pushing something else. And that's what happens in the classical algorithm. So with all of this sort of optimization, we get down to the algorithm in the Dragon book, or the last algorithm on the handout for CS241. And that's not the place you should start to understand things. The place you should start to understand things is at the beginning of the talk. So this is my last slide, except for the references. And here's the points I want to make. LR parsing is hard. It just is. I mean, there was no way I could make it beautifully clean and simple. It's hard, but it's harder if you start with the totally optimized thing and all the, it's like, you know what they do with pigs when they slaughter them? They cut their throats and hold them up by one leg, and they drain all the blood out of them. And what's happened is the highly optimized thing is really great for implementation. It's fast. It's great. But all the intuition has been drained out of it, like the blood has been drained out of a pig. And if you really want to understand it, which you should as a student, you should start from something that's a little easier to understand and then optimize it. And the other thing I wanted to underline is that there are a bunch of easier lexers and parsers. We should teach some of them, and we should get students to play with them. And finally, although I really didn't lean much on functional programming, the approach of defining functions that are mutually recursive, which mathematically is perfectly reasonable, and everyone here is a math student, that approach can facilitate the understanding of both Lexing and parsing, in my opinion. So here are some of the people whose work I've discussed today, and there are probably others that I've left off the slides. And if you want some of the references specifically, I can provide them to you. That's my talk. Thank you. Yeah, I'll put the slides online. And then you can find like typos in them, because I'm sure there are some.
So in the classical constructions, they have the GLR parser. They're not penalized for parsing ambiguous grammar, CFG. So they're linear for unambiguous ones and cubic for all of CFG. I'm wondering for you, here's one that's, I think you said LR0 is cubic, and the functional stuff.
The LR0, no, the LR0 should be linear. It's just, the last one that was cubic would be a recursive ascent. But once again, people have done research on how recursive ascent works on certain classes of grammars. It's faster. This would be something where an empirical study would really help. And there is a fair amount of literature on recursive ascent parsers. I didn't go all the way into it myself. But it's certainly something I think we could hand to a student and say, okay, try some typical grammars and see how long this thing actually does take. Is it cubic? Is it linear? What's going on here? And I don't know much about GLR, to be honest. I know the references exist, but I haven't gone into that end of things. This is not my area of research at all. It was just, I wanted to see, there's got to be a way of doing this better. That's what I wanted to discover. And, you know, this is just a few weeks of research on my part. Other questions? Okay.